Welcome to Spring LIB.
Okay, so we're in chapter 35, problem 43. So we have this figure here where white light passes through a diffraction grating and first and second order visible spectra, which we consider as rainbows, which appear on a wall 32 centimeters away. And each of these first and second order spectra have widths labeled L1 to L2 spanning across the rainbow from red to violet or vice versa. And it says that the rainbow wavelength is given from 400 to 700 nanometers, which is ultra or violet light onto red light. And we want to see which order of the rainbow, L1 or L2, is a larger distance. Okay, so we find the angle for each boundary color by using equation 3513, which tells us that the tan theta is equal to y over the distance to the screen. And what we can also find is using the normal diffraction equation, sine theta is m lambda over d. Okay, so how do we put this together? Well, what we can do is we can just figure out what theta is and plug it into here and solve for what y is, because we're looking for y components, because L1 is given by y of red minus y of violet, just by the distance here, because this is the y-axis. I'm going to put comma ones here because I said L1. Okay, so that means we need to solve these two equations for what y is, and we see that y is given by L tan of inverse sine of m lambda over d. Okay, so we should know everything here, so we can just plug this in. So L1 here is now given as L times tan of inverse sine. So for 1, we're using the first order, so m is 1, of lambda red over d. This is minus tan of inverse sine of lambda violet over d. And we can find this out. So what we do is we just plug this in, so 0.32 times inverse or tan inverse sine, red light is 700 nanometers. And what is our d? So we get 610 lines per centimeter. So if we rewrite that, this is the same as 1 over 6.1 times 10 to the 5 meters, or 1 over 6.1 times 10 to the negative 5 meters is our d. Okay, so let's plug that in. So 1 over 6.1 times 10 to the negative 5 meters, or 700. I'm going to rewrite this as 10 to the negative 9 meters. Okay, so let's subtract off our other one, tan inverse sine. Now we have 400 times 10 to the negative 9 over 10 to the negative 5. If we plug all that in, we get L1 is 0.0706 meters. Okay, so now let's just do the same thing for L2. So L2 here is going to look very, very similar, but there's going to be an extra factor of 2. Is all the difference here. Over 1 over 6.1 times 10 to the negative 5 meters. And then let's subtract off the violet term. 2 times 400 nanometers over RD times 10 to the negative 5 meters. And then we can just plug this in. And what we get here is L2 as 0.3464 meters. So already L2 here is much bigger than L1. It's around 5 times the size. So that's a much longer rainbow, or the rainbow is dispersed over a much larger distance.